Experts are confident that the James Webb Telescope will mark a turning point in space exploration, dividing it into a time before and after its launch. This comes as no surprise, considering that the groundbreaking discoveries made by the most powerful telescope in history have already revealed discrepancies between our existing models and the true nature of the cosmos. Webb has identified numerous structures that, according to our current understanding, should not exist in their observed form. This is especially true for objects that emerged right after the so-called Dark Age, appearing far too large and massive for such an early stage of cosmic evolution. And so, it is that experts are increasingly admitting that our established ideas about the early universe are hopelessly outdated and that there is still a long way to go before we will have understood this confusing era. In the thousands and thousands of objects that sparkle at us, giving it a gravitational influence that shapes the fate of nearby objects, a striking example of this occurred in 1994 when the 2 kilometers wide comet Shoemaker-Levy 9 ventured too close to Jupiter. The planet's gravity not only captured the comet but also tore it apart, breaking it into several fragments. By the time the fragments impacted Jupiter, they were already scattered, marking the first ever direct observation of an extraterrestrial collision. Interestingly, Shoemaker-Levy 9 had been captured by Jupiter roughly 2 decades earlier and orbited as an active comet, a phenomenon also observed for the first time. However, its orbit eventually brought it perilously close to Jupiter's surface. The resulting tidal forces shredded the comet, and just a year later, its fragments collided with Jupiter at an astonishing speed of 60 kilometers per second, over 210,000 kilometers per hour. The collisions with Jupiter produced fireballs that exceeded 23,000 degrees Celsius in temperature, rising an incredible 3,000 kilometers above the planet's edge. The most intense impact created a dark scar stretching 12,000 kilometers, about the size of Earth, and released energy equal to 6 million megatons of TNT, over 600 times the power of the entire world's nuclear arsenal. While other impacts have been less extreme, they have been observed and documented, supporting the idea that Jupiter serves as a cosmic shield, protecting the inner planets from devastating collisions. Jupiter's influence extends far beyond its massive gravitational pull, offering breathtaking celestial phenomena that intrigue astronomers. One such phenomenon is auroras, which are not exclusive to Earth. While Earth's auroras are visible to the naked eye, they shine brightest in ultraviolet light. The Hubble Space Telescope, capable of detecting ultraviolet wavelengths, has allowed us to study these mesmerizing light displays on other planets. Among them, Jupiter's auroras are the most easily observed, as the planet is not only the largest and closest gas giant but also possesses a remarkably strong. An astronomical paradox arises when considering the existence of certain galactic structures. These formations were already present just 500 to 700 million years after the Big Bang, yet they had already reached the mass of our Milky Way. Each of these 6 premature galaxies contains more than 10 billion solar masses of stars, with one even exceeding 100 billion solar masses. To explain the existence of such massive galaxies at this early stage, either the density of matter in the young cosmos would have to be 2 to 5 times greater than predicted by the standard cosmological model, or the galaxies would have to have grown in a way that is completely unknown to us. In view of this, it's probably not particularly surprising that the galactic mysteries henceforth became known as universe breakers. But in truth, this was only the prelude to a series of no less confusing Webb discoveries that have since given scientists a severe headache. On the one hand, there is the galaxy named JWST Z140, which entered the cosmic stage as early as 290 million years after the Big Bang, presents itself as much too large and starry for that time. How a galaxy could have formed several hundred million solar masses of stars in less than 300 million years is an open question. It's worth considering that fact again. Before the James Webb Telescope revealed the true face of the young universe, experts assumed that there were only tiny, low-mass baby galaxies at that time. In theory, of course, this also makes sense. After all, our models suggest that so shortly after the Big Bang, there simply wasn't enough normal matter to form so many stars in such a short time, and yet there they are, just like the red monsters that were detected a few weeks ago and once again challenge our understanding of early galaxy growth. Is the standard model of cosmology wrong? In view of the constant stream of new surprises that the universe now reveals with increasing regularity, a fundamental question arises. If so many structures are found out there that blatantly contradict the standard model of cosmology, could it be that this model is simply wrong? Now, to find out for sure, a research team led by Mangan Xia of the University of Geneva has set out to systematically search for the early outlier galaxies once again. In the course of this, the scientists evaluated the data collected by Webb's Near-Infrared Spectrometer, NIRCam, and in it, they actually discovered 36 more massive, dust-enshrouded galaxies that existed around 1 billion years after the Big Bang. Ultimately, Webb's high-resolution spectra penetrated the dust veils that made the galaxies practically invisible in the optical spectrum, whereupon the team set about analyzing the corresponding stellar mass and its relationship to normal and dark matter. In the course of this, however, 3 objects stood out clearly from the galactic mass, and because of their astounding size and red color, the astronomers named them the Red Monsters. In fact, the members of this trio are almost as massive as the Milky Way, and they also present themselves as extremely prolific star formers. Expressed in figures, this means nothing more than that the respective star formation rates amount to 795 to 1.30 solar masses per year, which, however, only further deepens the already existing mystery. To produce so many celestial bodies in such a short time, the 3 red monsters have to convert much more gas into stars than usual. To do this, the researchers state that their so-called conversion rate is 2 to 3 times higher than would be usual for the most efficient star formation in younger galaxies. This is because such galactic youngsters can only use around 20% of the available gas for star formation. But the red monsters have apparently somehow managed to circumvent the numerous processes that normally limit the efficiency of star formation. What does this discovery mean in a larger context? Well, for the Standard Model, it provides encouraging news. After all, an impossibly high density of matter in the young universe is not necessary to explain the existence of the early massive galaxies. At the same time, however, the red monsters suggest that star formation and galaxy growth took place quite differently back then than they did later. According to Shia and her colleagues, they provide strong evidence that the cosmos was 2 to 3 times more efficient in terms of galaxy growth in its early days. But what enabled it to do so is still completely uncertain. What is certain, however, is that the red monsters mark the beginning of a new era in the study of the early universe, and that not only the cosmic past but also the present appears extremely confusing. Webb shows that the universe is expanding too fast. As we all know, the universe has been expanding continuously since the Big Bang and at an ever-increasing rate. To explain the accelerated expansion of the cosmos, experts have postulated dark energy, which is thought to act as a kind of counterweight to gravity and about which, apart from that, practically nothing is known. However, the exact rate at which the universe is currently expanding is hotly debated, even though we actually know a fundamental cosmological constant, the Hubble constant, which indicates precisely this. Unfortunately, there is a significant problem here. The Standard Model predicts a Hubble constant of around 67 km per second per megaparsec. To put things into perspective, a megaparsec is approximately 3.26 million light-years. This means that, theoretically, the speed at which galaxies drift apart increases by 67 km per second for every 3.26 million light-years. However, real astronomical observations, based on supernovae, gravitational lensing, and variable stars, suggest a different value for the Hubble constant, 73 km per second per megaparsec. To clarify, this translates to an astonishing 20,000 km per hour per megaparsec. But how can such a significant discrepancy be explained? Could it be due to measurement errors? That's precisely what Adam Rees and his team at Johns Hopkins University in Baltimore aimed to investigate when they used the Webb telescope to reanalyze data originally gathered by the Hubble Space Telescope. The conclusion drawn from Webb's most extensive dataset to date was clear: the universe does not behave as theoretical models predict. Once again, the results pointed to a Hubble constant of 72.6 km per second per megaparsec. According to Rees, all evidence suggests that our understanding of the cosmos is still incomplete. It's possible that we've overlooked a key factor that provided the early universe with an unexpected boost after the Big Bang. Alternatively, dark energy might have undiscovered properties, or perhaps exotic particles are lurking in the vastness of space, waiting to be uncovered.